Hello and welcome to Taiwan Talk, a show where we speak with people living in Taiwan and Taiwanese people living abroad. I'm the host, Trevor Tortomasi, and joining us in the studio today is Sascha Zeegers, a researcher at Taiwan's Academia Sinica, whose work focuses on interstellar dust and maybe some star formation. Thanks for joining us today, Sascha.
Thank you.
Okay, I was going to ask you, if you know about star formation, how do I become a star? Okay, let's skip that question. We'll circle back to that.
Sure.
So you've been working closely with Academia Sinica in Taiwan. How long have you been working there?
So I came here in January of 2019. So it's, more than 3.5 years now, I think.
Okay, wow.
Yeah.
Big part of your life.
Yeah.
Okay, and what has been the focus of your team's research? Can you kind of bring us into like what you've been looking at recently?
So what our team at Academia Sinica of IAA is looking at or studying is the interstellar medium. So everything that is between stars, all matter and stuff and radiation and things that are there.
Does that this might be a really silly question. Actually, all my questions might be really silly questions. Does that include stuff between galaxies, or then do you just call it intergalactic and not interstellar?
So as long as you're within a galaxy, you call this like the interstellar medium, so medium between stars. There's also the intergalactic medium, so that's the stuff between single galaxies or galaxies.
And is that so different that it would be a completely different field of study?
There's much less stuff there.
It does seem that way, doesn't it?
Yeah.
Okay. So moving on quickly before I embarrass myself, how did you come to choose Taiwan for your work?
Actually, I was here in 2013 for the first time, and it was a big conference on interstellar dust. This was the start of my PhD research, and then at the end of it, the person, Sascha Zeegers, who was working here on interstellar dust, she said, do you want to do a postdoc here on interstellar dust, which was the topic of my PhD. So I thought that this is perfect. So yeah, I moved here in 2019.
And can you tell us about exactly how big Academia Sinica is? Because I know it's more than just cosmic study, but there's also a lot of other stuff. Like what is your department like?
So our department, I think, is very versatile. So they work on parts of telescopes, but also on the research. And this is really a nice combination of things. And I really enjoyed that you have both the developing parts of telescopes and the research as well, because you get really an insight in how things work. And I think IAA at Academia Sinica, the Astrophysics Institute and Astronomy Institute, is really on top of that business. They're involved, for instance, in the ELT, the Extremely Large Telescope that they're building in Chile.
I love the names scientists get to give some of this stuff, because they get to make them up on their own and like, hey, we're smarter than you guys, so we get to decide what to call it. We're going to call it the Extremely Large Telescope.
Yeah, I don't know where this is going to stop though.
Yeah, exactly. What do you call the next one?
Yeah, so we have already the Very Large Telescope,
okay.
Right? So there had to be something that topped that. So it's extremely large.
And so most of these telescopes are outside Taiwan, but you're processing the data here?
Yeah, so when such a facility is finished, then you also get the opportunity to observe with them. And then that data comes back indeed to Taiwan, and then we process it here. But yeah, sometimes you have to actually go there and observe. So that's also what some of the astronomers at Academia Sinica are doing.
Okay, that's awesome. So for what you're studying, which is specifically or mostly interstellar dust, I'll ask this question in the simplest way I know how. Space big, dust tiny. How do you observe something that we might think of as very, very, very small so far away?
Yeah, so indeed, these dust grains that I study, they are like 0.1 micron sized. So they're very, very tiny.
Whoa.
But there's also a lot of it. So that
It seems
helps.
like you might need the super duper extremely large telescope for that.
Yes and no. We have a kind of a disadvantage that we're sitting here on Earth and that all the exciting features of interstellar dust in spectra of stars that So what happens is you look at the star and then on the way there's a lot of dust. So your star is slightly obscured and you can make a spectrum of the star and you see the tiny features of dust in that spectrum. And the most interesting features in the spectrum are, if you look at the whole wavelength range, are in the infrared and in the X-rays. And everything that's well absorbed by the Earth is in that little infrared range, by the atmosphere of the Earth, I should say. And the X-rays, of course, they also don't reach the Earth because, well, that would be very bad for us if we got a lot of X-rays here.
So infrared is at one end of the light spectrum, right?
Yes.
One far end. For the
very red
Roy
part.
G. Biv, it's in the R. And then the X-ray is it the other end? Or
That's the other end, yeah.
The other end,
yeah,
okay.
The very energetic part.
Okay, wow.
So there are space telescopes that we use. Yeah. So I don't get to go anywhere.
Well, you don't need to go anywhere, I guess, because there's a 7-Eleven down the street. Okay, I'm assuming most interstellar dust isn't just made out of the same stuff, but like how different does it get out there?
That's actually a question that we can't really answer yet.
Okay.
Yeah, so we're looking at that.
You mostly just know it's there, but you're kind of still trying to map out what it is?
Well, we roughly know what it is. So we roughly know that you can compare it to soot, so carbon, like very small carbon grains, like cigarette smoke. On the other hand, you have, and that's the major part of it, stuff that looks like sand, but then very, very teeny tiny small sand grains, silicates. And for instance, a very dominant component of that is olivine that you might know from the beaches in Hawaii that look a bit green. And it's also in the ring of my finger.
That's awesome.
And here on the necklace.
Oh, heck yes. So you got some dust on your accessories. So this stuff, it's from the Big Bang and then gets made and has not been made into stars yet, or is this stuff coming off of stars?
So this stuff is really made by stars.
Okay.
Yeah, so when the Big Bang happened and when the universe was expanding and the first stars were generated, these stars are completely different than the ones that we have in our galaxy nowadays. They're the first generation of stars, and they're the producers of dust. So in the beginning, you didn't have any of these heavier elements. They're produced by stars. And if stars get old, they start to swell up, and a lot of chemistry is going to happen, and a lot of stuff gets dredged up out of the star and into their atmospheres, and then it slowly condenses. And these are quite light elements like silicon, carbon, magnesium, oxygen, and iron. A little bit. In the end, the star will eventually die. So what will happen is that part of the star will implode. And depending on how big the star is, you'll either get a black hole or a neutron star. And this either is a very violent event or not that violent. But what will happen in any case is that the outer layers of the star will be blown away. And all that stuff is given back to the medium around it, and can form new stars.
To other stars.
Yeah, it can form new stars. We think that that's like the basic components of dust.
Okay, so recently, I've read that your team recently had a project approved to use the James Webb Space Telescope, which was launched last year and then released its first pictures earlier this summer, on July 12th, to use the JWST for your upcoming project. Are you allowed to tell us about the project or exactly what you're looking for?
We are looking with the James Webb Space Telescope at 12 stars. And those stars are not that far away from us, but have quite a distance from us that there is stuff in between us and the star.
What's not that far away in sort of cosmic terms?
So it's not the center of the galaxy.
1,000 light years?
Oh, it's always hard to convert this to light years. So what astronomers do, they use parsecs. I have to do the conversion.
Oh man, I've got to look up parsecs again, because the only time I ever hear it is in like Star Trek or something. And then I never know, why is it better than light years? Or why is it easier than light years too?
If you look at the star in the sky during the year, you'll see that the position of it is slightly rotating.
Around, right?
Yeah. That is because the Earth is going around the sun. And you can measure the distance toward a star in that way by seeing how much it deviates. So if this wobble that the star makes is large, the star is quite nearby. But if it's very far away, it's almost standing still. And this conversion of getting the distance from that goes with the angle and the amount of movement it makes is easier to express in parsec, which is the unit of that. So that's parsecs. But light years makes more sense for if you just want to interpret how fast is light going and then how far away is it from us. So I think if you do 3 times the amount. You get light years. So our stars are at 2 to 3 kiloparsecs. So there's 2 to 3 thousandths of these parsecs.
Okay.
So yeah, it's quite a distance
it's
away.
It's quite far away. Okay.
Yeah.
So you're studying these, you said 12 stars, and
Yeah.
they are in our galaxy.
They're in our galaxy, and so in between us and the star, there's a lot of dust. So we selected sightlines that are diffuse, so you can still observe the star, but they're still quite dense, that you find dust features in the infrared there. So we're looking at these silicates and these carbon features, and then we want to determine what kind of stuff is it? What type of silicates? What happened to the silicates? So some of these grains, they might have lost their crystalline structure. So when they're made by stars, a percentage of it cools in a way that you get crystalline features. But if they're crystalline grains, but if they're in the interstellar medium, they get bombarded by radiation, by particles, and they might lose that structure. Or they might even grow in the interstellar medium. We don't know. And
grow because they're like gravity sort of brings them together.
Yeah.
Okay. Yeah.
And they're in this like denser environment, and they might clump together. Yeah, so the structure of these grains kind of tells you their history, so what they've been through in this violent environment. And we want to see if we can put limits on what they endured in the interstellar medium, or how they grew there, or yeah. It will take a while before James Webb will give us the data still. So in February, we might get the first data.
Ooh.
Yeah.
That's so exciting.
So we're doing preparation work. So that's what the day looks like, preparing for this.
Okay.
Building up databases with stuff that was measured in laboratories to compare later on with the stellar spectra that we get from James Webb.
Yeah, I saw that they're going to do I think it was like their Instagram page or something, but they're going to do like a talk. Ever wonder how we process the pictures we get from JWST? Here's a black and white one, or like actually it comes in black and white, and here's how we color it, and they're going to go talk about the process. So like some of the things come in as pictures, right? Or do all of them actually just come in as squiggles and they have to interpret it into pictures?
There are several instruments on JWST. So there is the camera MIRI, there's NIRCam, and then there is a spectrograph, NIRSpec, so that observes these spectra. MIRI also has a spectrograph. So then these instruments, they all do a different job. So one takes pictures and the other does the spectra. And so the nice spectacular things you saw were the pictures taken of
which is the easiest for most people to be like, look, it's pretty.
But what they also, so what they will talk about, I think, is how do you color this? Because it's infrared. We cannot see there. So we have to basically take our own colors that are further away in the spectrum and move them to where James Webb is now. So for us to interpret this, and then people say, yeah, it's fake colors. Well, yeah, it's fake in a way, but how would you see it otherwise? Otherwise, it's just a black and white image.
It's like taking a dog whistle that humans can't hear and then readjusting all the sounds so that you're hearing the same grouping of sounds but just lower register.
Yeah, just lower it.
And so then they're doing that for the eyes. Okay, that totally makes sense.
But you have to set the limit somewhere. So that's what they'll explain, I think.
Okay, that is awesome. I'm looking forward to it. What is the difference between maybe the telescopes here on Earth, like the very large telescope, and the JWST? Obviously, that one gets less interference from Earth's atmosphere out there in space, but are there advantages to some of the very, very large ones we have here on Earth that you use specifically?
Yeah, absolutely. There are differences and advantages. If you build on Earth, you're not really restricted with the size. You can build something as heavy as you want. Whereas if you're going to send it in space, every kilo is millions of dollars that you add to your project. So you don't want to do that. I think with James Webb, they built it as light as they possibly could, but also as big as they possibly could, right? Because it's unfolding, and this whole difficult space origami going on. So that makes it also complicated and more costly. So you can build a telescope on Earth that is way bigger than James Webb currently is for the same amount of money. So there is this balance, but then from Earth we cannot always see the same thing. it's much harder to observe. You have to open the box of tricks, but the very clever tricks of how to compensate for what the atmosphere of the Earth is doing. And we're becoming very, very good at that. We're able to observe planets directly around other stars. Because we are so good at stabilizing this stellar image. If you wouldn't do that, the star is like wobbling all around your image.
There is so much to think about. Also, I really love the phrase space origami. And I'm going to try and find ways to use that in my everyday life.
Okay. So the nasty thing about telescopes, they always have deadlines. So they keep coming. So if you go on vacation, they're not going to wait for that.
Right, yeah.
So
because they have 10 other teams that are waiting to use the telescope as well. Or...
well, they want to make schedules. So
right,
if you have time, then you need to put your schedules in.
Okay.
So these deadlines, they're scattered through the year. So the more telescopes you're using, the more deadlines you give yourself.
How many telescopes are you using?
Oh, yeah. Okay. So for the James Webb project, we want to characterize these stars very well. So for that, we used a very large telescope in Chile.
And the
so
JWST.
That's optical, and so infrared, JWST. Then you go to optical, that's Hubble and the VLT. And then you go to X-rays, and for the X-rays, we use XMM Newton and Chandra.
Okay.
Those are the two space X-ray telescopes. I want to also look at the X-ray part of the dust story. That's a different study because we cannot use stars for that because they're not very bright in these X-rays. But if you use X-ray binaries, those are binary stars that revolve around each other. But one of them is a neutron star or a black hole, and the other one is an evolved star or a normal star, and there's matter like drawn from that star in a disk, going in a disk, and the gravitational energy from that generates lots of X-rays. And these X-rays, they also go through the galaxy when some of them reaches us,
right,
and get absorbed, scattered along the way by dust, and also generate features that are very significant for the type of dust that's along the way. So you can look at the composition, the size of the grains. These things combined give you sort of a fingerprint of the dust composition and crystallinity that you can also observe with it.
And do you have a telescope at home?
No.
Oh no, you're tired of. So okay, so you don't. Once you're off work, you're kind of like, I
actually just never brought anything or bought a telescope in Taiwan. But
okay.
When I was in the Netherlands, I used to be a volunteer at the older observatory that they had in Leiden, like the old one with the antique telescopes.
Is that when you put your eye to? And you...
Exactly.
Oh,
and you
man,
look
okay.
through. So sometimes you need some kind of a reality check, right?
Right, yeah.
So if you look at Saturn through a telescope, for instance, it's so much more real than when you see an image of it made by someone and then you see it on a screen. If you see this through a telescope, it feels completely different. I don't know have you seen Saturn through a telescope?
I have not. No, every single first of all, I don't own a telescope, and I really am starting to think that I should. But I think
go
I'll
do
start.
that. It's nice. Yeah.
All right, get telescopes, everybody. Earlier this month, on August 2nd, the JWST released a new picture of a strange cartwheel galaxy. And the description in the picture, it looks sort of like almost like if you were to cut an orange in half, and it has like an outer ring of really bright, at least in this picture, sort of reddish glow, and then reddish glow in the center that was really, really bright too. And they talked a lot about sort of the interstellar dust in this galaxy lighting up parts of it. Have you looked at this picture?
Yeah, I've seen the picture. It's really nice.
So my question is, they talked about dust in this picture sort of lighting up. When does dust light up and become part of the picture? And when does dust just kind of obscure our observation?
So that really depends again on the wavelength that you're looking at. So with James Webb or JWST, you can really look through these clouds a lot. So you can see the stars that are behind it, and you see much more of the glowing if the dust is warm. So that's really also why we moved to this wavelength, because you can observe far more than with Hubble, where things were much more obscured by dust. So yeah, it's really depending on the wavelength, but also on what kind of environment the dust is.
Okay. And then another question I wrote, which now seems a little bit silly, but it's kind of how long can dust just sit there before gravity brings it together? Just thinking about all that dust out there, it makes me wonder, why hasn't that dust just collected and formed into stars already?
If you compare how much gas there is versus how much dust there is, then if gas is 100%, then dust is only 1%. So
okay.
there's not that much of it, but it dominates a lot of the processes in star formation. And it's kind of accelerator of this process. So if you have a dust cloud that's very big, very diffuse, a lot of radiation can penetrate, not much is happening. But usually in these clouds there are certain parts of it that are slightly denser, and these might be the starting points of where gravity can take over a bit and start to contract these clouds. And if they're contracting and there is a dust in these clouds, dust can cool the cloud and it can shrink more easily. It goes faster. And dust just shields this cloud. So you got a lot of chemistry going on. And then eventually, maybe if your cloud is heavy enough, it contracts that much that it can form a star inside. So not a silly question at all.
Okay.
Dust is important in all these steps.
Okay. And then are there parts of the galaxy that are kind of just dustless? Or is it so pervasive that you can always find a little bit wherever you look?
I think you can always find a little bit of dust everywhere you look, because we're also in our solar system and there is dust all around it. So I don't think that you can look in dustless direction. It will always be there a little bit. So we want to know what the composition of this dust is, right? Because in the end, we are made of stardust. So if you want to understand life and how planets form and how a solar system forms, you need to know the basic ingredients, like the starting stuff. And that's what we start with this project. What is it that goes into the whole star formation, like into the birth cloud of the star? And another important part is it different in different parts of the galaxy? What if you change the composition slightly? You end up with a completely different sort of range of planets. We want to understand how rocky planets like the Earth form, but what if you change the composition of the dust slightly? Do you get the same planets or not? And how homogeneous is it throughout the galaxy? Maybe it's not. Once we can answer that, you can make your models a lot better and start to understand way more of this whole process that we currently don't know.
And understand how the heck we all got here.
Yeah.
and why our galaxies look so the way they do. Okay, then this is sort of a tangential question, but like when humanity finally attempts interstellar travel, or even maybe for satellites that are really getting out there, how much do we have to worry about just the ever-presence of dust hitting whatever is trying to travel really fast? It seems like it's impossible to avoid.
Yeah, I haven't thought about interstellar travel that much because I would never undertake it.
Okay, that's fair.
But on the other hand, there is always this possibility that you encounter a grain, big or small. Once you're outside of our solar system, these chances are very limited, I think. Most of the dust here is because it's a remnant of the very dusty disk that was once there. But there's still grains out there, and that can be dangerous during your travel.
So what is the most difficult aspect of your field of work?
I think it's the steps you need to take. When we start comparing models, because we build models and we compare it to our observations, you have to put a lot of trust in these models. Now, these models rely on laboratory measurements. So first you have to understand this whole lab process, which is on Earth. It's not comparable to space. So then you have to adapt these and make them into dust models that are comparable to space. I think that jump between making the models and comparing them to what you see, that's really the hard part. But then what you get from space might be a surprise, and you have to go back to the lab. So it's kind of a cycle you go through. And the more you observe, the more you learn.
And you're going through this cycle, luckily, with a whole team of people who are working together.
Yeah,
Does
luckily.
that make it easier or harder?
It makes it easier because everyone knows something and can help others when you're stuck. So that's great of being in a team. And this team consists out of more than 30 people. So we have a lot of expertise there. Yeah.
Dang, 30 people. That is awesome. And these people are all at Academia Sinica right now, or are you talking about the other project with JWST? Or is it the same team?
This is JWST, the project. Some of them are at Academia Sinica, but a lot of us are just scattered all over the world.
Okay. I love when humanity teams up on something like this. That's just so nice when we can all look at the same thing for a bit.
Astronomy is very peaceful.
Yes. Okay, I guess finishing it off, what are you most proud of so far?
Well, I think this project, because it was quite difficult to get to select the sources that we wanted to look at. What are we able to observe within this project? And we pulled it off within the whole COVID misery of 2020.
Oh, yeah.
Submitted this proposal and then got the news that we were selected.
What was the application process like for JWST?
You write a proposal of a few pages because a lot of people are submitting these kind of proposals. So they have to be concise and they have to convey the message very clearly. So this takes actually a lot of work. Summarizing stuff is hard. So we wrote this proposal and it took us, I think, around 6 months to do the research about it, to condense it into this whole story and to submit it.
Wow.
And also you have to research the instruments and then show that you can actually do these observations, that you don't need a more sensitive telescope even than James Webb, or that it's that you could do it from the ground, that it's actually very simple. So yeah, you have to go through all these testing stages in your proposal.
So moving back to talking a little bit about Academia Sinica, from your experience working there, what do you think Taiwan's place is in the future of cosmic research?
I hope Taiwan gets a big role in it, and it already has. So I hope they retain that, of course. Mm-hmm. The institute where I work is building the telescopes and doing the research. I think that's something that's so valuable, and that Taiwan has that. And it's one of the most prominent institutes in Asia. It's really great.
That Taiwan gets to focus on that is already a good thing.
Yeah, and actually there are a lot of astronomy institutes in Taiwan. I don't know, there are more than 5. So.
All right, well, I'm apologizing to any non-science oriented listeners, but there's going to be more science episodes coming up in the future. So. Okay, and finally, is there anything you'd like to say to people living in Taiwan, anyone who might be interested in astronomy, or any young people listening who might think about a future in science?
Yeah, if you're interested in astronomy, please visit the open days that Academia Sinica is organizing. Yeah, if you have any questions, I think you can always email the institute and follow the dream. If this is your dream, becoming an astronomer, don't think I'm not smart enough or I don't know if I can do this. You can do a lot if you put your mind to it.
And then you'll find hopefully a team of 30 other people who also want to do that.
Right. Yes.
And want to help you. I think this is all fascinating. And thank you so much for the hard work that you've done.
You're welcome.
And thank you to Academia Sinica for allowing researchers to focus on all this awesome stuff and get the news out to the world. And thank you, Sascha Zeegers, for coming in joining us today.
Thank you.
And this has been Taiwan Talk. Until next time, I'm Trevor Tortomasi on ICRT FM 100. If you'd like to hear more from ICRT, you can check out our other podcasts. We've got Taiwan This Week, a roundup of the news in Taiwan every Friday, English in the News for useful English expressions explained in Chinese, and EZ News, spelled with the letters E and Z, for simplified daily news. For some lighter news in both English and Chinese, check out News Bites and News for Kids. And if you enjoy them, tell a friend. Thanks for listening.